Hi, good morning. My name is Melissa Miller, and I'm here to moderate this session and join in just a little bit as well. I want to introduce you guys to our session panelists here today. So here, the first gentleman here on my left is Lukas Rowland. Lukas is the Battery Energy Storage System Lead at HDR, where he leads a diverse team in deployment and design of battery systems to build a more resilient grid. In 2021, he received RMELS, or is that how you say it? Yeah. RMEL Emerging Leader Award. Lukas is a licensed professional electrical engineer and received his degree from the University of Michigan. Welcome, Lukas. And then the next gentleman is also my boss, and his name is Eric Stoutenburg. He's the Director of Energy Storage for Eolian Energy, and he leads strategy for our portfolio of development projects, including originating new projects, commercial efforts, and project development. Welcome, Eric. Myself, I'm Melissa Miller, as I mentioned, and I'm responsible for the development of activities at our company in the central United States, primarily in ERCOT and SPP. And I am an established energy and renewable energy developer with 20 years experience of renewables energy experience starting in 2002. So I started out as a landman, actually knocking on doors out in West Texas 20 years ago. And it's been a really interesting career, going from focusing on wind and then in solar and then now in batteries for the past year and a half. And it's been a really interesting and fun experience. So learned a lot here today so far, and we hope that we can bring to you some great information about this new use, this new technology, and the opportunities that it brings to our grid. And we just kind of, before we got started, wanted to get a poll from you guys and learn a little bit about the audience. So I would ask you, don't raise your hands yet, but the categories would be if you are a utility with a utility, if you're a developer, policy, regulatory person, landowner, stakeholder, or maybe you're just in the wrong session and you wanted to be in net metering. So if so, hopefully you'll stay with us. So if I get a show of hands for anybody that is representing a utility here. Wow, that's amazing. How about a developer? Okay. Policy, regulatory? Great, thank you. And then how about any landowner or stakeholders? Okay, welcome. So I'm going to go ahead and hand it over to Lukas so he can get started with his part of the presentation, and look forward to it.
Thanks, Melissa. I didn't hear any boos when she mentioned University of Michigan. I was kind of bracing myself, but thanks for being kind. We are going to talk about battery storage at somewhat of a high level today, focusing on utility scale energy storage. I'm going to focus on more of the technical and engineering side, talking about what the technology is, what it looks like. Eric and Melissa will talk about the use cases, the applications, and go through some example projects. First, quickly, HDR, a lot of you in the room might be familiar with us as a company. We're headquartered over in Omaha. And we do a lot of things, but in the battery storage field in general, we've been involved in the industry for, in one fashion or another, about 10 years. And our services are pretty broad, including the detailed engineering, owner's engineering, development support type of roles, feasibility studies and IRP support, and all of the things that kind of go along with that. So fire and life safety, which we'll talk about briefly. Obviously an important part, environmental support, environmental permitting support, construction support, and strategic communications, all a part of our service offerings for battery storage projects, big and small. When we talk about battery storage these days, we're almost always talking about lithium-ion batteries. This is essentially the same technology that's in our pockets, in our laptops, increasingly in our vehicles these days. And those industries, the portable electronics industry in general, has really driven down the cost of lithium-ion battery technology aggressively in the last basically 2 decades, which unlocked this as a technology to be scaled up for grid scale applications. When we talk about lithium ion, that's really an umbrella term. There are a number of chemistries or subtypes of lithium ion batteries that fall into that umbrella. And each of those chemistries has their own mix of performance and cost, safety advantages and disadvantages. So just a few of them are shown on the screen there. Two of the top two that we tend to see in most grid scale applications are lithium iron phosphate, LFP, and nickel manganese cobalt, NMC. There's a whole slew of other technologies, but those two have been far and away the leading, most popular choices for grid scale. There are some pros and cons between those two, between energy density and power density, obviously cost. There's some thermal runaway considerations to look at as well. There's a little bit of a higher threshold for thermal runaway for LFP than NMC, although there's still a lot of variability between specific OEMs as well in terms of their performance, safety features, and cost. So it's just important to note that there are a lot of choices out there when we say lithium ion, and not all of those technologies are created equal. What's in the box? So this is, I'll say, a bit of a dated graphic, but I still like it because it still shows kind of a nice cut-up of what goes into a typical lithium-ion container. Most utility scale applications are still outdoor, containerized. There's been a lot of discussion in some projects that are at large-scale indoor facilities, but by and large, most deployment in recent years has been outdoor in containerized systems. So these, about 5 years ago, were primarily the ISO container, the steel box, 40 or 53 foot ISO box that was then sort of retrofitted with racks of battery modules, which were packages of battery cells. Those are all wired together in series and parallel onto one DC bus within the container. And then in most cases, that container has a single DC output. There are some OEMs that are integrating the inverter or power conversion system within the container, in which case you have an AC output. But still, most OEMs, most products now are a DC configuration. The vast majority of the contents of the box are obviously the batteries themselves, but you have a number of systems that are there to maintain the health and safety of the batteries, the HVAC being a very critical one. On this diagram, there's one on either side. Generally, lithium-ion batteries are pretty particular about the temperatures that they operate in. Much like us, they prefer room temperature, more or less. And if you can keep them within that tight bandwidth, then they last much longer than if they deviate. If you charge and discharge them on high or low temperatures, then you get some pretty serious degradation behavior. So in order to maintain that, some very robust HVAC systems are generally required for these containers. That's, again, a prefabricated system. There are liquid cooling options as well, which have their own pros and cons. But in general, it's very critical to have climate control within the enclosures or wherever the batteries are housed. That system is in most cases is going to require an auxiliary power supply, an external power supply. There are some instances where that's pulled off of the battery DC bus internally, but by and large, another thing to think about with site design is that auxiliary power supply and how where you're getting that from, how you're metering it, how that's being accounted for in your round trip efficiency. All kinds of things about aux power supply that are fun to explore. But I also called out there's the fire suppression tank. It's a tank in this example. There are all kinds of ways of suppressing battery fires, some more effective than others. That field is worth its own presentation, but we won't go too far down that road. But I'll just say that there are codes and standards that have been developed and evolved to require specific fire safety and fire suppression mechanisms within batteries. And there's a lot of options for different types of suppression. The industry has started to evolve a little bit in terms of how the containers are designed. A lot of the tier one suppliers are moving towards offering a more cabinet style architecture rather than the basic shipping container that we were seeing about 5 years ago. One of the biggest advantages of this approach is really to make the systems as prefabricated as possible. You used to have to ship the container on site because it was too heavy to ship with the batteries installed, and then install the racks, the modules after the containers on site, and then test it and certify everything on site. So just drew out the construction period quite a bit, whereas when everything shows up tested and certified, it's a lot more plug and play this way. Augmentation is another, or degradation rather, is another very important thing to consider with lithium-ion batteries. They, much like your cell phone battery, if you've had a phone for, if you can make it last 4 or 5 years, which I'm never able to, but the battery doesn't last quite as long as it used to. It degrades over time, right? There are all kinds of variables that play into that rate of degradation, but by and large, the biggest one is just how it's used, how it's cycled. The more you cycle it, the more it's going to degrade. Different OEMs, different cell manufacturers will be able to project their degradation, and that degradation projection is generally used to provide some sort of strategy, some plan for accounting for degradation over the life cycle of a project. So a lot of approaches to that. One being just simply oversizing the project when you install it. So in this case, 4 megawatt hours or 400 megawatt hours, you would install maybe 450, 500 in usable energy, and then ride the degradation curve, monitor that over time. And then periodically throughout the project, you could then augment or add additional battery containers to the system to boost the energy capacity back up and then basically play that curve. There's a lot of strategy to that, a lot of different approaches to augmentation, a lot of kind of cost benefits to think about. But generally, one thing to consider early on in a project when you're going through the development phase and looking at different battery vendors and technologies and going through an RFP process, perhaps, knowing your use case, which Eric will talk about, knowing specifically how you want to use the battery, how it might be dispatched, is really useful upfront for projecting degradation and then planning for it. If it's not well understood how it might be used, then it can make it more difficult for vendors to size the system appropriately to account for degradation. What do they look like in terms of layout? So they are very modular systems generally. Very kind of, you have one iteration and you repeat the same thing over and over. The example on the left is an ideal situation. We're starting to see a lot more sites that we're trying to fit into interesting shapes, and you have to do some more creative things with the layout. But generally, it's a very rectangular kind of, place all the equipment as close as possible to your point of interconnection, within a substation if it's small, or outside of the substation if you're, say, paired with a solar array. There's just a lot of flexibility in it. And there's flexibility in power and energy ratio as well. Generally, you're seeing most lithium systems kind of pre-configured for 1, 2, or 4 hours. But based on how that C rate is, how the power to energy ratio is laid out, you're going to have different quantities of containers and their associated inverters and transformers, et cetera. So the ratio of pieces of equipment is going to change from one project to another. One thing to mention here is AC coupled versus DC coupled. So that's referring to coupling storage with solar. There are some, on paper, some theoretical advantages and disadvantages of going with DC coupled. I think most systems we're still seeing are AC coupled, but DC coupled is considered. And one, from a layout perspective and design perspective, one thing to think about with DC coupled is that when you situate your batteries and pair them with the solar inverters, those solar inverters are going to be scattered throughout the site. So you're going to have groupings of batteries that are also scattered throughout the site. So your energy density, the amount of land you require for the battery, is going to be impacted by that. You can't locate everything close to the substation per se with a DC coupled system. As they get bigger, again, it just continues to scale modularly, and what you end up with is quite a large amount of cable and conduit in a very dense area. So this is one thing that I think sets it apart somewhat from solar and wind, is that there's just a lot of power being pushed through some small areas. So being having an accurate design and thinking through how that cable and conduit is managed, and that the appropriate D-rates are thought about, and that the installation methodology makes sense and is basically thought through sequentially to account for just how much is going in the ground in a tight area is really important. You've got your main powertrain, DC and AC. You also have auxiliary power that I mentioned earlier to think about running to every single battery enclosure. If you have a water-based fire suppression system, you may have mechanical piping for that, for the sprinkler system to think about. So you end up with some pretty dense site design. From a technical standpoint, generally where the industry is headed, or things that are going on recently, I'd say the biggest thing this past year or two has just been scale. The size of the industry as a whole is doubling or tripling in terms of the actual number of megawatt hours deployed. And the scale of individual projects is also going up. We're seeing a lot more 500 megawatt hour plus installations in one site, even a few gigawatt hour installations in one site. So it's growing rapidly. I'll let Eric and Melissa chime in if they disagree, but I would believe that the IRA would encourage more standalone storage due to the storage dedicated ITC, rather than having to kind of bootstrap the solar ITC onto a storage project and co-locate them to take advantage of that. So we will likely see more standalone storage projects for that reason. More prefabrication, as I mentioned, there has been a lot more kind of plug and play type of product design from the battery standpoint, also from the inverter and transformer. The skid configuration is becoming very common for large scale installations. And it's all designed to cut down on installation and testing time and just make the system as straightforward as possible to design and construct. Fire codes I mentioned a bit earlier, but they have been developed and iterated through NFPA 855 being the prevailing and code that's designed specifically for, or was developed specifically for, battery energy storage systems. The International Fire Code, the latest revision, more or less mirrors NFPA 855 in terms of what's required. And there's a new version of 855 that came out recently. And that's being adopted more often across the country in different jurisdictions. It's somewhat challenging from a fire code perspective to keep up with that adoption rate and to understand what codes are actually applicable in certain jurisdictions. It's generally still a case-by-case situation where different fire marshals, different counties, et cetera, may adopt different versions of code, right? And then they may have their own modifications to the code. So there's some research required up front to ascertain what is going to be required for that particular project. The actual technology itself, there's a lot going on in the R&D space for batteries, looking for different cathode chemistries and anode chemistries, different ways of improving energy density, driving costs down, improving safety, improving or reducing degradation, that sort of thing. So there are different ways that you can do that. What it all is going to come down to is essentially cost. If any of these new technologies in the lithium space can scale fast enough to drive their costs down, then you might see some of that start to get deployed for grid storage. But I'll say that the vehicle industry is also I'd say the primary driver in a lot of that R&D for lithium storage, and the bulk of the supply chain for lithium-ion batteries is going to be going towards the vehicle industry. So I think the grid storage industry is going to kind of follow that to some extent. And then you get into this realm of non-lithium technology, which has been kind of stuck in the R&D and pilot phase for quite a long time. A lot of companies have some interesting technologies, flow batteries and other types of non-lithium battery technology that are promising on paper. They've struggled to be cost competitive with lithium, but given how that kind of landscape has changed recently and the price of lithium is not what it used to be, and the EV industry and the pressures of that are probably going to persist for a while. There's some at least speculation or increased consideration of some of these alternative battery technologies for grid storage And that might be a little bit more of a competitive space in the near future, but time will tell. I do have a quick slide on just a generic architecture for what a flow battery is. I'll just say that the general difference is that you have, rather than packaging hundreds of thousands or millions of individual pre-manufactured battery cells, as with a lithium system, you're more or less building one giant cell, right? And you're kind of deconstructing that system, and you have a fluid electrolyte, one that's a cathode, one that's an anode, that are stored in two tanks, and then you pump them across a ion exchange membrane. So it's, from a chemistry standpoint, a lot like any other battery. You're just supersizing one cell and then pumping that electrolyte fluid. So that comes with some advantages or perceived advantages. But again, it's still, a lot of these technologies are in R&D and pilot and looking to scale right now. This is a quick demonstration project that we supported in Washington for a vanadium redox flow battery that amounted to 8 megawatt hours, 2.2 megawatts. Again, that familiar shipping container style that was very popular back then. But I'm going to wrap it there from our perspective and give it back to Melissa. Yeah.
Great. Thanks, Lucas. That was really interesting. Appreciate it. So we're going to talk a little bit now about Eolian and our company and the work that we're doing in the United States around large-scale battery energy storage. And as I mentioned earlier, I oversee the development of the central region of the U.S., which is ERCOT in Texas, and then SPP. We have quite a few projects here in Nebraska as well. And then Eric Stoutenburg, the Director of Energy Storage, is going to join me after I give a little bit of information about the company and talk more about use cases for battery energy storage. So Eolian, the company, we own and operate a portfolio of storage projects, and we also have about 21 gigawatts of wind and solar that we're invested in across the United States. And you can see on the map the distribution of all of those projects. And you probably notice immediately that the central United States is a very important part of the country for us. And listening to the different sessions over the past 2 days, one of the things that stuck out for me is the conversation about the distribution of resources for rural and urban, and we all know that that we've got an intermittent resource with renewables, and so what we've seen is a lot of the renewable energy has been built in the central U.S. along the western edge of that central United States, and a lot of the population centers and the load is actually on the east, and so the storage that we're bringing to the market for our company is exclusively standalone. And so we're targeting areas that are specifically targeted to help to balance out the power grid and provide resiliency. And we have a few projects that are, 2 projects specifically that are operational, and another one that will be coming online next year. And I'll tell you a little bit about those. One of them is in a more urban, very urban, and so we've kind of mostly targeted urban areas for that reason, for that redistribution of the power and providing support for the power grid. So this project, Silverstrand is an 11 megawatt project. It was our first project. It came online in 2020, and Silverstrand is also a 4-hour duration, so 44 megawatt hours, and it's in Ventura, California. And what's not shown in the picture is that about a block away from this facility is actually the Ventura County Fire and Police Station. It's about a block away, and so this is just a great representation of the possibility of building battery storage in a city. This project, the Chisholm project, it's 100 megawatts. It's 125 megawatt hours. It's in Fort Worth, Texas. It started operating in 2021, and it's within the city limits, and it's on a heavy industrial parcel, But one of the things that's interesting, even though it is in a heavy industrial zone, we still needed to work with the city in order to get some zoning changes. And so the presentations that we just heard right before this one were really relevant for this use. And the zoning and permitting is still evolving, and I think more presentations, personally, I think more presentations like the one that we're doing today that Lukas just gave and that Eric's going to share are going to be really informative for framing up policy and understanding more about the use. So the more that we can be in communities and be learning more and sharing is going to be really beneficial, for actually implementing these projects. This project here, the Moderator project, it's a 200 megawatt, and it will be a 200 megawatt and 514 megawatt hour project that will be coming online next year. It'll be the largest large-scale standalone battery storage project outside of California. It's in Mission, Texas, which is just south of McAllen, Texas, near the border. And it's located next to a DC tie to Mexico. Right now, we're not looking to transmit power to Mexico, but placing battery energy storage in specific locations that are, in between different grids that you're seeing some congestion or opportunities to support other power grids is one of the unique opportunities that batteries can provide, in addition to providing that balance to other forms of energy just in general. And so with that, I'm going to hand this over to Eric, and so that he can give you a little bit more information about the use cases of batteries.
Great. Thank you, Melissa. In the interest of time, I will skip over the lessons learned and return to those at the end, because going first definitely has its lots of lessons we can pass on to those that are going next. So let me skip through those. So what do these rather boring looking boxes do? And my kids make fun of me because I used to be in the Army, and then I worked on wind turbines. At least they're tall and they move and they look cool. And then went to solar, and it's kind of boring actually after a while. They're just kind of panels there. And now we're just sort of boring boxes. But what they do is actually really the cool part. So the analogy that people often use is that they're sort of a Swiss Army knife. And that's because they can do a lot of different services: capacity, energy, ancillary services. And I'll speak to those in a minute here. But I think it's kind of important to contextualize what battery storage contributes to capacity and reliability. And the example I like to use is, if you could choose, a coal plant with a winterized coal supply, and you could choose reciprocating engines, which might be a similar fast response capacity resource, or you could choose 4-hour duration lithium-ion storage. The question of which one of those is better depends on what the scenario is. So if you're looking at 2 days of a cold winter front, you're probably going to select the capacity from the coal plant. There still may be a need for storage during that period of time, because you can then let all your thermals run at their best heat rate set point and leave ancillary services obligations on the storage resource. If you then switch to, as a gentleman, Casey from Southwest Power Pool said yesterday, tomorrow there's going to be a big wind ramp. We know the wind ramp is coming. We rarely know if it's going to be an hour earlier or later than forecasted. The resource there, the capacity resource, meaning it's dispatchable and responsive, that you probably would choose to manage that event is probably storage, because it's short duration, it's quick, it can come online, and you go into that event either with a charge if you're kind of worried about a ramp down, or an empty battery if you're worried about a ramp up and you want to absorb some extra energy. Likewise, when we get to higher and higher penetrations of renewables, storage does what the other two don't do, which is consume energy. It is a demand response resource at that point. It can absorb and avoid curtailment of renewables and then supply to the system later. So that's why I think it's interesting when we get into the arguments of, what's the effective load carrying capacity of any given resource? Well, it's really a question of, what scenario are we talking about? And storage is really, although it itself is sort of the Swiss Army knife, it is also one tool in the Swiss Army knife of solving reliability generally. It does not solve all reliability issues, but it solves certain ones very, very well, particularly when it's fast and responsive. If you look at the interconnection queue for SPP, As of last night, there are still 124 battery energy storage projects in the queue. They range from 50 megawatts to up to 200 megawatts. The majority of the ones that Melissa works on are 100s and 200s. And that represents just shy of 15 gigawatts. I think the statistic yesterday was about a third of resources that enter the interconnection queue actually join and become operational. So that means 4 to 5 gigawatts of resources will come to SPP in the form of standalone storage or those paired with renewables, wind, solar, or as often the case in Texas as well, is they can be next to gas-fired power plants where the operator chooses to put the duty cycle of ramping on the batteries and allow the thermal machines to run at a more efficient cycle. So storage, sort of summarizing where it belongs in a portfolio, is it something that sort of plays well with everything? It isn't solely in the camp of it's just a reliability asset. It's not solely in the camp of just solving renewables, nor is it solely in the camp of supporting thermals. It's kind of this glue, this grease that kind of binds these cylinders that actually generate real energy from primary fuel sources, wind, the sun, and fossil fuels. Some of those use cases, you can see there on the graphic on the left. You do get either full or near full PQ curve capability from the inverters and storage units, so they can be great on voltage control and frequency response. Those are tend to be the seconds capability of these resources. One of our ERCOT projects was originally specified to have a response time of 250 milliseconds and have a very rapid set point onto a ramp rate that was established. And then you have, your minutes resource is sort of spinning reserves, other ancillaries, potentially black start, though it would be false advertising to say that all energy storage projects can do black start. That's a special capability that's usually built in after the fact. And then as you get to the hours, you're sort of in that place of power trading and capacity and integration of renewables. And so the next graph is sort of, the value stacking. And you can look through tons of, literature on this, and you'll see a bunch of what is completely fake curves. They are true. What it's really doing is just illuminating there's all these things that a resource could do. And what's actually not often mentioned is it's really important to distinguish that a different owner and a different storage project all have different stacks. And then most importantly, those change over time. And we have firsthand experience with that. If you jump into California, primarily you're getting really two bundles of revenue. One is resource adequacy or that flexible capacity bundle, and then the rest is market participation, primarily in ancillary services. If you go down to Texas, it's kind of a gold rush with energy storage right now. Everybody piled in, assuming they could just, at a minimum, hang out in response to reserve service, which is roughly equivalent to spinning reserves. And now that you have that many batteries online, and that's a thin market product, it's several hundred megawatts up to a gigawatt, you're already seeing saturation of batteries doing that. So as you begin to plan for storage, you need to look at not only what it might have done in the past year as a guide for what it'll do in the first couple years of operations, but to begin to look ahead for what market reforms might occur that might change what products are available. How is my own energy supply portfolio changing? Maybe it's becoming more renewable, or maybe I'm losing one big thermal unit, but I'm adding also reciprocating engines. How are those all going to play well together? Because it's quite dynamic. And that's maybe the benefit of storage is it's a Swiss Army knife, which means you can actually cut yourself on a bunch of tools, but it also can adapt to whatever you're eating. You're trying to kill a squirrel because you're stuck in the woods, or you're just trying to pull a splinter out of your finger. A little bit more on ERCOT, since that's primarily been our experience to date, and has similarities or translations over to SPP. If you could put a battery through the interconnection queue and actually get on the system, you'd make a tremendous amount of your revenue just doing ancillaries, primarily regulation in SPP. But again, if 4 to 5 gigawatts of storage come in, you don't need 4 to 5 gigawatts of storage doing reg. You only need 500 megawatts to a gig at any given moment. So you will see a gold rush that'll be slower in SPP because the interconnection queue is a large inhibiting, sort of barrier, whereas in ERCOT, it's sort of, you can get through the queue quite quickly and almost saturate things. And you're beginning to see that. So summer revenues were tremendous. There were days where we made as much as we can make in a month. And then September is sort of the doldrums. And that's reflective of too much storage got added to the system too quickly. And then as our traders have adapted that resourcing, we begin to do other products. So you definitely have to go into these things with a mindset of, you know, what is the full scope of what it can do? You also then, engineer and design the system to be able to accommodate that, and then be very attuned to, participating in the market committees of what's coming up with products. The ramp rate product is an interesting one for storage, the uncertainty one in SPP as well. Touching just briefly on commercial structures for storage and SPP, and this is broadly true for everywhere. So on the left, you're seeing sort of categories of risk and options. And on the top, you're seeing sort of various agreements. And there's obviously utility category or utility ownership category. And then there's an agreement category where the third party is going to own the resource. And then you're going to do something with them. So if you choose to either develop your own asset as a utility or purchase a development asset where developers assemble the interconnection, the land, and the permitting, and potentially is bringing the battery supply for you, you're going to own it. You're going to wear the development risk, which is not trivial, particularly when there isn't code written for most zoning rules for storage resources. You're going to wear the operational risk of managing degradation and augmentation, as Lukas mentioned. But you're also going to pick up, it's your resource, and you're going to dispatch it, which means you capture all of the benefits. And the payment structure is, you sort of, lump sum it and you're done. On the other end of the extreme, and this is more true of how California is primarily set up and other places, is the utility just engages the third party to provide one specific service. So in California, it's resource adequacy, which is their version of capacity. And that's great because then it leaves all of the risk with folks like us who have many, many projects. And we know from the beginning, not all of them succeed in the development phase. And we usually have a portfolio of operating projects to manage risk operationally. So that's maybe a great starting point. You can just say, hey, I need either peaking energy. So just provide me a, on-peak block for 2 hours or 4 hours, or be there and become SPP accredited capacity. And you have the 4-hour duration requirement as well as transmission deliverability studies. And then as you kind of, go through those in translation, a full tolling agreement, those are quite common for the utilities we work with in the West. We carry kind of all of the risks of ownership, and however, the utility has the keys to the optimization and to the dispatch. So they deploy it for whatever they need at the time, transmission, ancillary services, and most likely and more often capacity. And then obviously there's a bit of a gray area in here with the build transfer, especially given that it's, quote unquote new technology and there are, like Lukas mentioned, evolving standards. It is sometimes nice to say, look, why don't you just bring the resource all the way to COD and I'll take it from there. It's, I'm a lower cost owner because of our source of capital. I'm a long-term owner operator as a utility. So you do have that sort of menu in there, and you tend to see really large utilities maybe start on the left. Most utilities start on the right and progress left as they become more familiar with it and let the risk reside with third parties and private capital. Now let me maybe jump back real quick to our lessons learned. So that first one is, and I kind of highlighted this throughout, is, the economics and market rules will drive the use case, and they will be very time dependent. So just go in from the beginning with not worrying about, am I going with the Tesla system or what the battery chemistry is? Truly start with what is the need I'm trying to solve for, and that'll dictate everything else going forward, and then also look over the horizon. So dispatching the plant is non-trivial. So the first one is that sort of economic decision-making and risk assessment. We have folks on our team who have traded power plants, coal, nuclear, gas, wind, solar, combined heat and power plants. They now operate our battery storage projects because it is a bit of a trader mentality of assembling your bid offer curve volumes and what products you want to be in and price, and then assuming those obligations from the day ahead market in the following day in real time. And there's a little bit of optionality mentality. There's a bit about risk management. Obviously, when you're in the private sector, you can take a little bit more risks and do virtual trading and things like that. One thing we did learn is there are no shortage of firms out there that will promise you, a PhD with artificial intelligence and machine learning can perfectly dispatch your thing. We have fired many of those firms from working on our projects. And they're all great firms, and I don't mean anything derogatory to them. It's just that it was a little bit of a learning curve and a little bit of, and this is sort of true broadly, everybody wants to throw AI at everything. It's just not true. They don't tend to manage the risk profile of your obligations when you're trading. And so you really want to have somebody who is, committed to the resource and worrying about really that bottom one. You're kind of doing this multi-variable optimization for what your storage dispatch will be the next day. Generally speaking, though, the primary variable is managing your state of charge. You want to have either, you want to be at 50% because you might have a direction up obligation or a direction down obligation, or you're going into a risk period where you're going to put the battery at full charge because you may be serving several hours of ancillary calls or an energy obligation. And then the middle one was definitely probably where we got most of our bruises and extended delays on timing, including one shipment of batteries that got stuck behind the boat that got turned around the Suez Canal. That was a 2-month delay to one of our projects in Texas. But so they're really, and Lukas can kind of confirm this or rearrange it a bit, but there's about 4 systems. There is the battery management system, which is really monitoring cell health. What's the voltage of all the cells? What is the temperature on all the cells, both for maintaining warranty obligations, but also in avoidance of any risk of thermal runaway or fire. Then you have sort of your energy management system, which is common to any solar plant, any wind plant, any gas plant. That's a sort of easy part. And that's doing, all your control set points of real and reactive power and breakers open, breakers closed, et cetera. Your third system is your scheduling coordinator, or in ERCOT, it's your qualified scheduling entity. That's really doing the interface between what the grid tells me to do and what I'm telling the battery to do. Again, fairly simple. And then the fourth one is who or what is making the economic decision of what the battery should do. And the breakdown has generally been between either the BMS, which is sometimes provided by certain vendors, and your EMS provider. There's can be a breakdown there. I would recommend if you're doing a first project, I think it took us our first project and our third project, we did it this way. The vendor for the EMS and the BMS were the same. That's really helpful. The second project where those are split, that was painful. And then the one that has been quite challenging is the interface between what I mentioned earlier is the economic decision making, telling the scheduling coordinator, this is what we're going to do because that's the obligation we have with the market, and then telling the EMS to do that. We had one of vendors, they didn't even report state of charge of what they expected the resource to do based on the bids they have assembled. So really, when you plan these projects in your backup of the economics, market, and use case, spend some time with your IT and control systems folks and really synthesize, like, if I want the battery to do this, do I have the systems in place? And have I spoken through all of the coordination to make that actually occur? So that's sort of the end of our presentation. I think we have a bunch of time for questions. So, yeah.
Thanks, Eric. All right, so I'm going to kick us off with questions, and I'll just throw a softball for you guys to see what you think. It might be a hard ball, I don't know. What are the best practices for fire and emergency responders?
That's a loaded question. I'll just put it that way. But best practices, yeah, that again, it's worth its own presentation. But I think the key things at a high level to think about are early engagement with the HJ and coming prepared for that engagement with a detailed project design, or to the extent that you can, is really important. Understanding the codes and doing some education. Not just to, the developer, the owner, the EPC, but also to the actual, in a lot of cases, the fire departments, the fire marshals themselves, especially if you're in a rural area, it's never seen this type of technology before. There's some education involved there to get them comfortable with the safety features and the tests that are available to sort of prove out the safety features of battery storage systems. The key one being UL 9540A. So there's a UL certification 9540, which references a testing guideline 9540A, which is basically a simulation of thermal runaway for a battery storage product. They start at the cell level and they work their way up. The results of that test are basically what can be provided or should be provided to a fire marshal to understand the safety features and understand that if, in a lot of cases, if I have a fire in one container or one cabinet, it's not going to spread. And here are the test results that demonstrate that. And then those results and the safety features all drive the rest of the conversation about what type of suppression is going to be required. What are my setback requirements? What is my emergency response plan? So that's another one, is developing an emergency response plan specific to that project and that technology. Again, gives more comfort to first responders to know how to respond when there's an incident, if there's an incident, and to feel prepared, because that's what they're inevitably looking to do.
Yeah. Only thing to add is we always start with, an asset is never worth a life. So these things are just, they're unoccupied. We don't need firefighters to enter them to stop the fire. They're supposed to, effectively self-control and self-emulate themselves. And so there's no residual energy left at them. And then coming in with, hazard mitigation analysis and a draft emergency response plan, just give the fire, marshal comfort that this is a typical industrial use. Could it burn? Yes, as all things could. And here is a plan for if that, rare event does occur.
Thank you. I think we're ready to take questions from the audience, and it looks like there's one right here next to the microphone.
Eric, you did a good job kind of hitting on some of those use cases, which I always find fascinating because I don't understand them all. But kind of two-part question there. What are you guys seeing in SPP, maybe specifically on use cases? I think you talked about the ramping was a good example of what might be useful. And then also, you also touched on this a little bit, but in practice, how does that work with the dispatching and the I think it's a day ahead market, but could you explain that a little bit too?
Yeah, certainly. Most likely, from what we see, and actually we're working on projects in development at SVP, you're going to see a combination of ancillary service obligations, primarily in regulation or spinning reserve. The ramp break product is probably also ideal for storage. And then you will see probably bilateral arrangements between utilities and developers, the same way you would with a gas plant, to provide, SVP accredited capacity. And that ironically almost ends up looking like the very well-established business model in California, where utilities looking for capacity because they have that resource adequacy requirement to SVP. But utilities are supposed to serve customers with low-cost power. They're not supposed to be, taking risk trading positions. And so that's best left for, that revenue capture is best left oftentimes with a private developer who has that risk appetite.
I have a son that lives near Dallas, and certain times at night they get free electricity. And they're thinking of getting, an in-home storage battery. So, what do you project and look at the future? Is it going to be mass storage, or is it going to be people like my son, a lot of homes with electric cars or those kind of storage units?
Yeah, I'll field an informed but just personal opinion. So we focus primarily on utility scale because the cost savings are tremendous. So I have solar on my house. I do not have batteries on my house. I have an electric car. I think that's the only batteries I need. I did recently look to expand the solar on my roof because I wasn't hitting 100% with my electric car load. And I asked them what the price of the Tesla Powerwall is. And when I convert that back to $1 per kWh, it seems insane for ratepayers to pay systems that are 4 to 5 times expensive on $1 per kWh than what you can do at utility scale. So economies of scale are just, they dominate. The other one I think is maybe more relevant is, batteries are energy intensive to manufacture. They do require, mining as does anything that's built. And so the best use of a battery is by a utility or a system operator optimizing it for the system's benefit rather than for one narrow customer to optimize it for their particular benefit. In the example of a home, if I put storage on my house and it's because I'm trying to balance when I'm not at home, but my solar's producing, but if my neighbor's working from home, why wouldn't it's more efficient for my solar to just go over to my neighbor? And so it's about more like a system optimization issue. the way that utilities in some parts of the country with on-peak and off-peak pricing and time of use, particularly like places like California, there may be an economic incentive where you could just pay for the crazy, domestic consumer batteries and make an economic case. But broadly speaking, if we're really trying to address lowering emissions and lowering costs and improving reliability, my view is more batteries belong in the hands of utilities at distribution level or utility scale. But again, it's just a personal opinion, and there's probably arguments both ways.
Two questions. One's a quick follow-on to that one, and then a separate question. The quick follow-on is, do you have any observations about Green Mountain Power purchasing or helping to share the purchase price of those at-home batteries?
Yeah, certainly. So I have a home in Steamboat Springs, and it's a rural, mountain co-op, and they do a lot of rebates. And that's because they are collectively trying to avoid a demand charge from, their G&T. And so there may be reasons where it makes sense for rural co-ops and munis to incentivize their customers to do things that are effectively demand reduction. So again, that's sort of expanding the totality of the economic question. And so that might be a great use. When I think of, having lived in California at one point, when you think of like wealthy homeowners just thinking a Tesla Powerwall is cool and it saves them a little bit of money, that isn't usually my flavor of them actually doing something particularly good. But a program delivered by a utility that's actually accomplishing either that distribution circuit's demand response or collectively for the co-op, then it can make sense.
Great, thanks. So I'm struggling. Thank you very much. It's very informative. I love your grid there with utility-owned and third-party and the risks there. I'm thinking about transition. How does a utility transition? As you lay out all of the potential uses for batteries, then I see stepwise investment also bringing on a lot of operational knowledge needs. How do we build the workforce? You can't just keep layering on additional duties for people who are already savvy in how things are working. So talk to me about how that transition might take place.
Yeah, I'll ask you a follow-on question on that too. It's a great point. So we started with doing our first battery projects, developing them in 2017. So rather early, but not the earliest folks who sort of demonstrated its use in California back in 2016. And I would say that there are good consulting firms, but broadly speaking, the U.S. is deficient right now in a number of engineers who can staff to this. And that's actually true really generally of all electrical engineering. It's sort of a resource that's hard to come by. That's why while it may complement a business interest of ours, I would say very sincerely that the best place to start is to put all these risks onto a third party as a start. And then you sort of can create arrangements and agreements to be like, great, let's do a pilot project with you. You have the resources and have assembled the talent, and then learn from them and then begin to grow your own capacities. Because yeah, it is, like I said, the plant operator who dispatches, wind or solar or even a coal plant will be surprised when they come to batteries and sort of needs that experience. And it is out there in limited groups. And currently it mostly resides in third parties or some of the major utilities who've led energy storage stuff like Dominion in the East. So.
Yeah, and you mentioned pilot projects. I mean, that's, I think, a common sort of tool that's used by a lot of utilities to get familiar with a new technology and how to operate it. There's, from our perspective, we've supported enough pilot projects now that it seems, and the industry has been around for long enough that it seems there should be a certain amount of confidence in the technology that, any new utility to this space can borrow from others who have gone before them and kind of paved the way. But nonetheless, you still have to familiarize your own staff, your own operating standards, your own, personnel with something new. So that's where a small scale pilot project just to get to know the technology and how to operate it can be helpful. But having a partner in that process who knows the technology and has been through that process with other utilities can also be really helpful in kind of drawing on those lessons learned. So.
Yeah, I would also say, early engagement like we're doing at this conference is critical path as well. Like I know I was here last year and storage was not really mentioned very much at all. And this year it's been mentioned quite a bit. So that learning curve that comes from the participation in this room is, I think, really additive and important. So I think that we've been hearing that theme quite a bit.
Eric, in your presentation, you mentioned a limitation of a black start. What would be those limitations for a power plant that where the storage batteries couldn't be used?
Yeah, and you can maybe add on this as well. So generally speaking, when you go with a vendor, their inverters are not what they might call grid forming, where they can establish the frequency. They're generally in receipt of the AC frequency, and then they synchronize to the grid. And you can pay for options and telemetry and metering controls to facilitate that, but it doesn't come standard. So, yeah.
Given the huge increase in demand for battery storage that's happening now and will continue for the foreseeable future, how practical do you think it is that there's enough lithium to serve all the needs? And the second part of that question is, how do you think a viable pathway can be created for the use of these new battery technologies?
Yeah, it's a great question. A lot of studies have been done to sort of project what the demand might look like based on the growth rate of the vehicle industry and grid storage on all of those specific minerals. And actually, lithium, there is a tremendous demand for lithium, and the spot market is very constrained right now. But there is actually quite a lot of lithium available. It's just the demand and the price has not been high enough to sort of warrant the discovery and development of new refineries until now. So what we're going to probably see with lithium specifically is a lag between the high demand and the really high price points right now for lithium carbonate, which are then driving the development of new refineries and mining really all over the world, including here in the US. But there's a long time between discovery of a deposit, for example, and actually producing some final product that can go into a battery, depending on how you define that, 5 to 10 years at least. So there's going to be a lag in that for the lithium market specifically. Some of the other minerals that go into batteries, again, there's some R&D, a lot of R&D going into replacing some of those, reducing their quantities by weight to alleviate constraints on the market. So I think eventually we may get to a point where the lithium prices kind of calm back down, but there's definitely going to be a lag, I'd say. Yeah.
Yeah, well said.
Can you talk to us a little bit about recycling lithium-ion batteries?
Yeah, that's a good follow on, I guess, because that's the other piece of that puzzle that eventually will play a role is they are highly recyclable. The question is, do we have the capacity and is it worth the cost, right? But there are a number of companies that are setting up for this inevitable wave of recyclable, mostly vehicle batteries. And you can recover, depending on the type of battery and the mineral, upwards of 90% of that. And recycle that back into the supply chain very effectively. So that's been proven. Right now, it's just waiting for the price parity, more or less. Once that wave comes of expended fuel or expended batteries, then there will be enough supply to hopefully bring the price of recycling down. But it's something we know how to do, and a number of companies are preparing for that. Yeah.
All right, with that, well, thank you for your time today.